Hiyo! This video is going to take you through the structure and bonding derived grade exam for 2019. So question 1, solid question, and there will always be solid questions in there, so please learn your stuff. Yeah, there's 4 different solids and you have to learn all of those things. You need to know what particles are made of, what the type of bonding is, how the bonding actually works, and then you need to be able to link it to the properties that you've been asked about. So yeah, you just got to take the time to try and learn it. So first things first, we've got a little table where we have to try and identify a type of solid particle attractive forces. You should be able to look at the solid and recognize what it is. So start off with the easy one. If it is a metal, so such as magnesium, then it is a metallic solid. If it contains a metal and a non-metal, it is an ionic solid. If it contains only non-metals, then it's molecular, unless it's carbon, silicon dioxide, or unless it's diamond, silicon dioxide, or graphite. So in this particular case, we got one of those exceptions, and the exceptions are giant covalent network. Right, type of particles, what are the things that make up these solids? So giant covalent networks are always atoms, metallic solids are always atoms, and ionic solids are always ions. The attractive forces between particles in a giant covalent network, it is covalent bonding, it's in the name. Magnesium, metallic bonding, again it's in the name. Or you can write the electrostatic attraction, I'm going to run out of room, attraction between the nuclei and delocalized electrons. Okay, if you just write electrostatic attraction, it's not enough, you have to say what the attraction is between. For ionic bonds, for the ionic solid, it's ionic bond, or you can do electrostatic attraction between ions. Right, onto the meaty question. Explain why magnesium metal has a high melting point and is able to conduct electricity in both solid and molten states. Reference structure, bonding, and particles in your answer. So solid answers are always a kind of 3-step process. Number 1, you state the type of solid. Number 2, you describe its structure and bonding. Number 3, you relate the bonding to the property. So for magnesium, it's a metallic solid, which is made up of atoms, 3D kind of lattice grouping of atoms, how you want. Held together by a metallic bond. Which is a strong electrostatic attraction between the nuclei and the delocalized electrons. So I'm just going to stick that there so I don't have to type it all out again, because I'm pretty lazy. Okay, so that's kind of step 1 and step 2. Step number 3, relate the bonding to the property. So that attraction between the positive nuclei and delocalized electrons is very strong. And because it's very strong, it takes lots of energy to break. Because it takes lots of energy to break, it's got a high melting point. Alright, number 2 is conductivity. To conduct electricity, you need mobile charged particles. Okay, so if you're trying to work out whether something can or cannot conduct, you have to try and decide if it has mobile charged particles. So in our particular case, magnesium has delocalized electrons, which are free to move. And those delocalized electrons are irrelevant of state, so they're free to move in both solid and liquid. Molten is just a fancy term for liquid metal. So therefore it can conduct. In both states. On to part C. 2 of the solids listed in part A, so don't just make them up or give generic answers. 2 of the ones that we looked at in A can be described in the table below. So bends and dents, only metals will bend and dent. So magnesium is that one, and things that will shatter, we're after an ionic solid, which is lithium chloride. Technically the diamond can shatter as well, so if you did that we should have accepted it, but lithium chloride is the main one we're after. So we go through the same process, 3 steps. Number 1, state the type of solid. 2, describe the bonding, and 3, relate the bonding to the property. So number 1, magnesium is a metallic solid made up of magnesium atoms which are held together by a metallic bond, which is a strong electrostatic attraction between the positive nuclei and the delocalized electrons. Now I'm going to use poor form here and put as discussed in part B, rather than having to rewrite it again and make you guys sit here doing it. So it's metallic solid. So that's steps 1 and 2. Step number 3 is the metallic bond is is non-directional, which means it goes in every single direction all at once. When Mg is hit, the atoms can slide over each other. Okay, kind of like a piece of Play-Doh. When you hit a piece of Play-Doh, you pull a piece of Play-Doh, you can see the Play-Doh kind of stretches as little bits of Play-Doh slide over each other. That's what the atoms do in a metallic solid. And they do it without breaking the bond. So that's the important thing. So they slide over each other without breaking the bond. Alright, lithium chloride on the other hand is an ionic solid. It's a lattice of ions, of lithium and chloride ions, held together by strong ionic bonds, which is the electrostatic attraction between positive and negative ions. Okay, so that's step 1 and 2, ionic solid and a description of the bonding. Relating it to the property, ionic bonds are directional, so they only go in certain directions. If you think about the lattice, up, down, side to side. What this means is when it's hit, the ions can move. Like ions line up with like ions, so lithium ions line up with lithium ions, chloride ions line up with chloride ions, and they repel. So because they're the same charge, they repel each other, and therefore it shatters. On to question 2. It's looking at photosynthesis. So it gives you an equation. So 6 carbon dioxide molecules react with 6 waters to produce a glucose and 6 oxygens. This little thing here is the enthalpy of reaction. So what it's saying is when this whole thing takes place once, it's going to involve 2,801 kilojoules of energy. So number 1, provide evidence that this is an endothermic reaction. We know it's an endothermic reaction because the enthalpy is positive. So because the enthalpy of reaction is positive, that means it absorbs energy, which is what an endothermic reaction is. On to part 2, calculate the energy required for the reaction of 17 grams of CO2. So rather than dealing with 6 moles, we only have 17 grams. So, first step is to work out how much energy is going to be released when 1 mole of CO2 is reacted. I find this the easiest way to deal with these problems. So, 6 moles of CO2 releases 281 kilojoules of energy, then 1 mole of CO2 is 2801 over 6, which is 466.83 kilojoules. So if you had 1 mole of CO2 exactly, it would absorb 466 kilojoules of energy. Now, in this particular question, we don't have 1 mole, we have 17 grams of it. So if we convert 17 grams into moles, using the formula mass over mole mass, get 17 over 44, which is the information we're given, and you get 0.386 moles. So instead of having 1 mole of CO2, we have 0.386. So we take our 0.386, multiply it by 466, and we get our answer of 180 kilojoules to 3 significant figures. Okay, if you want to do it the other way, where you work out the number of moles and then multiply it by 2081, you just have to remember to then divide your answer by 6 to take into account the fact that there's 6 moles of CO2 over there. Alright, number 3, draw a labeled enthalpy diagram for the photosynthesis reaction showing the relative energies of products, reactants and products. So because it's an endothermic reaction, the energy of the reactants is going to be less than the energy of the products, because it has to absorb energy to turn into the products. And the difference between the two bars is your enthalpy of reaction. Now, to be safe, instead of just writing reactants and products, you should actually write CO2 and water, and then up here, glucose plus oxygen. Part B. When solid potassium chloride is dissolved in water, the temperature of the water increases. Circle the term that best describes it is exothermic reaction, because heat is released, and that is the reason why the water actually heats up. Number 2, use your understanding of structure and bonding in solid potassium chloride and in water to explain the solubility of potassium chloride in water. So this is actually another solids question, it's just in a different part of the paper. Still going to go through this same steps of number 1, identify the types of solid, number 2, describe the types of bonding present, and number 3, relate the bonding to the property discussed. So, KCl is an ionic solid. And again, I'm going to be lazy, but I really shouldn't, as discussed in question 1C. So it's made up of ions, which are in a big three-dimensional lattice held together by the strong electrostatic attraction between positive and negative ions. Water, on the other hand, is a molecular solid, which is made up of molecules of water, and they're held together by weak intermolecular forces. Okay, now for something to dissolve, the attraction between your solid and the solvent has to be stronger than the attraction between, or the attraction within the solid and within the liquid. Okay, so the attraction between your solid and the liquid has to be stronger than the attraction within the solid or within the liquid. So in this particular question, we need to remember that water is polar. And because it's polar, it's got polar bonds. So the hydrogen is slightly positive and the oxygen is slightly negative. So what actually ends up happening is the slightly positive hydrogen is attracted to the chloride ions, and the slightly negative oxygen is attracted to the potassium ions. Now I have to be clear here, I am using this little symbol here to represent that it's a slight charge. Do not call it ions. If you call it a hydrogen ion or an oxide ion, the marker is just going to stop reading and give you nothing. Because in water that is not the case. You just have a slightly positive charge and a slightly negative charge. Okay, so we've got these attractions going on, and what happens is the total attraction of the H to the Cl minus and the oxygen, what am I doing, to the K plus is greater than the ionic bond in the potassium chloride and the intermolecular forces in water. Okay, so the attraction between the hydrogen and chloride and the oxygen and the potassium, all of those little attractions all added up is actually greater than the ionic bond which is holding potassium and chloride together, and the intermolecular forces which are holding water molecules together. Okay, and further down the page I've got a little picture showing that. Okay, what you need to remember is it's not just a one kind of attraction. Each potassium ion is going to be surrounded by lots and lots of water molecules, which means lots of attractions, and each chloride ion is going to be surrounded by lots and lots of hydrogen atoms. On to part C. Ethane gas can be used as a fuel. They've given you an equation. Calculate the mass of ethane that must be burned to produce 1,350 kilojoules of heat energy. So we're going to go through a similar type of process. If you look at the equation, we have 2 moles of ethane. So 2 moles releases 3,120 kilojoules of energy. 1 mole of ethane releases 1,560 kilojoules. Okay, so this is normally one of the big tripping points that people have with these energy calculations. The first thing you should always try and do is how much energy is released or absorbed when 1 mole of whatever substance you're doing reacts. Right, so nifty little equation I use. There's a couple of different ways of doing it, but this is what I think is the easiest. The total energy release when this reaction takes place depends on two things. It depends on how many moles of ethane you have, and it depends on how much energy 1 mole of ethane releases. So I'm going to put enthalpy for 1 mole of ethane. Okay, and hopefully that makes sense. The more moles of a substance you have, the more energy you release. The more energy that's released per mole of a substance, the more energy that's going to be released. So in this particular case, we're told that the total energy that is produced is 1350. So that's the total energy. Number of moles of ethane is what we're trying to work out. And the enthalpy for 1 mole of ethane is 1560. So if you rearrange the equation, you get x moles equals, where are we? 0.865 moles. So what that's effectively saying is we need 0.865 moles of ethane. Okay, then using our formula, mass over molar mass, number of moles is 0.865. The mass is what we're trying to work out, and the molar mass is 30. Chuck that in your calculator, you get a mass of 25.961, which is equal to 26.0 grams to 3 significant figures. The other way that people might do it is you take the energy that you know is released, which is 1350, and you divide it by how much energy is released per 1 mole of a substance, which is 1560, and that gives you a ratio of 0.865, and that's equal to the number of moles of a substance, and you can then go through and do this step here. Okay, but this is effectively doing what I'm up here. It's just a slightly different way of, it's just written a slightly different way. Both give you the same answer. You just use what you're comfortable with. Okay, if you learned a different method in class, just go with that as long as it gives you the same answer. They're all the same. Lucky last, you're given 3 molecules and asked to draw the Lewis diagram for them. First thing you need to do is work out how many valence electrons you have. So fluorine is in group 17, which means it has 7 valence electrons. There's 2 of them. Oxygen's in group 16, which gives us 6 valence electrons. So that gives you a total electron count of 20. So first thing you need to do is put your atom in the middle. Because there's 2 fluorines and only 1 oxygen, oxygen is going to go in the middle. The other way you can kind of work it out is whatever atom is to the left of the periodic table, like furthest to the left, that will generally go in the middle if you ignore hydrogen. Okay, so whatever's furthest to the left is going to go in the middle. So lay out your atoms, put in your bonding pair, and then you fill up the outer atoms first to make sure they all have 8 electrons. So the rules for Lewis diagram is every single atom is trying to get 8 electrons. The exceptions are hydrogen, which only wants 2, boron, which is happy with 6, and beryllium, which is happy with 4. So fluorine is going to want 8, so we're going to give each fluorine 8 electrons. At this point we have used a total of 16 electrons out of our 20, which means we have 4 left over. So any remaining electrons you stick around the central atom. So there we go, each element has 8 electrons, 8, 8, 8, and we've used a total of 20 electrons, and we started with a total of 20, so we're done. Alright, CF4, carbon gives you 4, each fluorine gives you 7, 4 times 7 is 28, so it gives us a total of 32. Same type of process, put carbon in the middle because there's only one of them, put in your bonding pairs, and then you go around and fill up the outer atoms first. So give the fluorines 8 electrons each. Once we've done that, that gives us, we've used 32 electrons, we started with a total of 32, so that is us. HCN, hydrogen, gives us 1, carbon 4, nitrogen is in group 15, so gives us 5, It's a total of 10 electrons. So we're going to put carbon in the middle, it's furthest to the left. Put a hydrogen on one side and a nitrogen on the other. Put in your bonding pairs and then fill up your outer atoms. So hydrogen only wants 2, he's happy, so then we fill up the nitrogen. Now at this point we've used 10 electrons, and we only had 10 electrons to start with, so we've used all we had. But if you look at our Lewis diagram, carbon only has 4 electrons at the moment, so it's not happy. So we can't just leave the Lewis diagram like this because carbon needs 8. And we can't just add more electrons because there's nowhere for them to come from. So what actually happens is the nitrogen donates some of its electrons. Rather than this lone pair of electrons just belonging to the nitrogen, it's going to move them into the middle so that it is then shared between the nitrogen and the carbon. And when you do that, carbon then has 6 electrons, which isn't enough, so nitrogen then moves another pair from the top. And what it ends up being, if I redo it a little bit more clearly, it ends up looking like this, and you end up with a triple bond here, which is 6 electrons being shared between the carbon and the nitrogen. Right, part B, you're given 2 Lewis diagrams, determine the shapes of the 2 molecules and explain why they're different. Okay, we've got to be careful. I think they're getting a little bit more picky with this when they try and talk about explaining why they're different or comparing and contrasting, and you actually need a statement that explicitly states why they are different. With shape questions, it's kind of 3 main points that you have to deal with. Number 1, you have to look how many regions of charge are around around the central atom. So if we look at phosphorus, it's got 1, 2, 3, 4 regions of charge. So pH3, it's 4 regions of negative charge. So somewhere you have to state that it's negatively charged or that there are electrons, which implies it's negative. Okay, and these are going to repel for maximum separation or to get as far apart as possible. You can use your own words. And when they do that, they arrange themselves into a tetrahedral arrangement. Okay, and a tetrahedral arrangement is this kind of shape for those that have forgotten. Now, because 3 of those regions are bonded, 1, 2, 3, and 1 is non-bonding, 1, the final shape is trigonal pyramid. Okay, so that's talking about pH3. pH3, on the other hand, is different. So this is my kind of comparative statement. It is different as it only has 3 regions. Of negative charge. Okay, 1, 2, 3. Those 3 regions repel to get as far apart as possible into a trigonal planar arrangement. And because all 3 are bonding, the final shape is trigonal planar. Okay, so your 3 statements are how many regions of negative charge, they repel to get as far apart as possible into whatever arrangement, and then because there's X bonding, Y non-bonding, the final shape is whatever, and then I've got that comparison of why one is different to the other. On to part C, you're given 2 molecules and you have to explain the difference in polarity of the 2. So again, we've got some kind of key statements we have to talk about. We have to talk about, are there polar bonds / bond dipoles, and why do they exist? Number 2, how are they arranged? And then number 3, do they cancel or do they not cancel? So number 1, BH3 contains polar boron hydrogen bonds. And the reason why is boron is more electronegative than H. Okay, so that makes the boron slightly negative and the hydrogen's slightly positive. Okay, those polar bonds are arranged symmetrically. Around the boron. And when you're doing this, if you're after excellence, and sometimes you have to actually state what shape it is. So they're arranged symmetrically around the boron in a trigonal planar shape. And because they're arranged symmetrically, polar bonds cancel. And it is non-polar. Right, CH2O on the other hand, it contains CH bonds and CO bonds, which are both polar, as carbon is more electronegative than H. And O is more electronegative than C. Okay, so talk about why both bonds are polar. Now, what's interesting with this one is the bonds, the polar bonds are of different strength. And the reason why they're different strength is because all of the atoms have different electronegativities. Okay, so the oxygen is going to pull electrons differently to the carbon than the carbon pulling electrons compared to the hydrogen. Okay, and this is where language escapes some people. This is actually a symmetrical molecule, or the polar bonds are arranged symmetrically because there's three of them. They're spread around with angles of 120 degrees. So even though the bonds are arranged symmetrically, the polar bonds are of different strengths. And therefore won't cancel. And the molecule is polar. Alright, final one. D. Methane burns completely in oxygen. You're given an equation, and they're really nice because they've given you the formulas of the different chemicals involved. So the question itself, calculate the average bond enthalpy of oxygen to oxygen double bond using the information provided. So these types of questions, there's a formula you have to remember, and it's the enthalpy of reaction is the sum of all the energies of the bonds broken minus the sum of the energy of all the bonds that are formed. So the way I do it, step number one, write down your equation and then work out what bonds are being broken and what ones are being formed. Okay, so if we look at our equation, bonds broken, we are breaking bonds on the left hand side. We're going to break the carbon-hydrogen bonds, and there's 4 of them, and we're going to break the oxygen double bond, and there's 2 of them. And when we form bonds, we're forming CO2, so we're going to form 2 lots of the C double bond O bond, and in water we're going to form, each water forms 2 OH bonds, and because there's 2 moles of water, we end up forming 4 of them in total. So bonds broken is 4 times CH and 2 lots of O. And bonds formed, you've got 2 lots of C double bond O and 4 lots of OH. Okay, once you've written that, go through and plug in the numbers that you know. You're told the enthalpy of reaction is minus 810, so that's minus 810. You're told that CH is 414, so 4 times 414. Oxygen is the one we're trying to work out, so 2 lots of O, that's what we're trying to work out. C double bond O, you're told is 805. And OH you're told is 463. Okay, and then it's just a matter of using your calculator and plugging in all the numbers. So minus 810 is equal to 1656 plus 2 lots of O double bond O minus, that ends up working out to 3462. And then if you shift that over there and you shift that over there, you end up with 996 is equal to 2 lots of double bond O, and therefore your double O bond is equal to 996 over 2, which is equal to 498, and the unit for these is kilojoules per mole minus 1, because that's what they told us up here. So that is all the answers to the thermochemistry paper. Hopefully it's cleared things up. If you're still stuck, please ask your teacher and we'll do our best to try and help you out. Thanks for listening.